And make sure if you have questions, you ask them. All right. Does anybody have any questions or comments before I start? It should be straightforward, but you understand that with transmission lines, this is something, the reason he does transmission lines first is because all of you have been acquainted with circuits. So what you're doing is looking at the lumped element parameters, the R's, L's, C's, and G's, like you would in a circuits kind of problem. And you're familiar with that. It's not that foreign. Anyway, getting back to it, when we had transmission line, you don't need to write this down. This is just so I have something to refer to. A transmission line will have some inductance, some resistance, some conductance, and some capacitance per unit meter. This is not the best. Remind me to throw it down. And when we look at this, this is typically L prime, R prime, G prime, and C prime. And then we take a look at a voltage here. It's going to be some V of Z. This will be a phasor. It has a current I of Z that is also a phasor. And there is some loss current here, and that's delta I of Z. And there's some differential voltage that will be lost between here and here, and that's going to be a delta V of Z. You can forget the Z. And this is over a distance, delta Z. Now this is what I set up last time, and I told you the reasons for the development. All these things are the primes, they mean per meter values of capacitance, inductance, resistance, and conductance. From that, we had two equations we developed. It was dV dZ is equal to, you can put the minus sign here if you want, is minus R prime plus J omega L prime times I. And I'm not going to put the of Z in here, it's implied. And then you're going to have a dI dZ is equal to minus G plus J omega C times V. And those are the two equations that really govern the actual behavior of voltage and current on these transmission lines. Remember, they're constant cross-section, so neither R, L, G, or C changes with distance down the line. If they did, this would be a different kind of problem. So when we do this, we're going to get one equation with one unknown. And the way we always do it, we're going to take a derivative of either one with respect to Z, and then use the other equation to substitute in for the first derivative of the quantity that was by itself. So when I come here, if I take two derivatives of this, I'll call it equation 1. I get the derivative, second derivative V with respect to Z squared equal to minus quantity R prime plus J omega L prime. And then I have dI dZ here. Now y'all remember that from last time, right? I don't have to put the tilde there. Follow me on that, class? And the way we got rid of that dI dZ is we replaced it with this second equation. So then what we end up with is the derivative of V, second derivative of V with respect to Z squared is equal to, these minuses will cancel each other and they become R prime plus J omega L prime times G prime plus J omega C prime times V. And that's where I left off last time. Y'all remember this, class? Can y'all follow me? Just look at your notes and you'll see this is exactly where we left off. Next I'm going to do is, and we do this all the time in engineering, we try to reduce the amount of things we have to write over and over again by creating constants. Here we're going to create a constant, and it's called gamma. And gamma is equal to alpha plus J beta, but it's actually equal to the square root of R prime plus J omega L prime times G prime plus J omega C prime. So what we've done is taken this constant and simply equated it to all these here, gamma. Now gamma, does anybody know what the term, these are common in physics and in mathematics. This is usually termed the propagation constant. The propagation constant is alpha plus j beta, so they have to have the same, technically the same units. Alpha is called the attenuation constant. And beta, the j beta term here, this is called the wave number. Now you're going to see why they're called that in a second. So the propagation constant, if you look at this for a second, if you have real plus imaginary, and they're multiplied together, chances are good that you're going to have a real plus imaginary number. You're going to have a polar number in there. Y'all follow me on that, class? So that makes sense. So what we do is take the real part, we define it as an attenuation constant. The units of the attenuation constant are Napiers per meter. That's not that important yet. And plus j beta. J beta is a wave number. And wave numbers have units of radians per meter. Now a radian is a measure of angle. So that should clue you in that we're talking about a phase relationship. As soon as you hear radians per meter. I don't know what's going on with these lines. I guess they need to replace them. Anyway, and you'll get familiar with all this in a second. This is where I was last time. So now getting back to this equation right here. It looks like the second derivative of v with respect to z squared would be equal to gamma squared times v. I'm going to assume that we know v is a phasor form of something. It's going to vary with z only here. We're in the phasor domain. When we look at that, we can write a homogeneous second order equation. The second derivative of v with respect to z squared minus gamma squared v equals 0. This is a common equation that you had back in the days when you took differential equations. Now something I'll tell you right now, in engineering and physics, everything that we deal with, solve, design with, and everything deals with two types of equations. They're either integral differential equations or they're different summation equations if it's a discrete type of event. Differential equations are the thing that describe all natural phenomena in a continuous domain, you might say, if there's a continuum of values. And this is a standard differential equation. Now the solution of this you can get in a couple ways. Does anybody remember how to do these? One way is with an integration factor. Do you all remember that? You assume the type of solution, and because that's a second order homogeneous, it's a homogeneous differential equation. The form of the solution is what? Is some constant k, e to what? It would be e to the alpha z. Z would be the we do a few derivatives, then you find what alpha is in terms of gamma. Do you all remember doing this kind of stuff? What's the other way, anybody? Laplace transforms. Do you all remember Laplace transforms? Either one will do it. This would be a Laplace transform, but it wouldn't be with time as a variable. The time to a s, it would be what? It would be spatial to s, and some of you haven't been acquainted with that yet. Anyway, there's several ways to get this. It's a very common problem. The solutions, and Wentworth does this in his book, but the solution is this is pretty straightforward. V of z will have some value, v0 plus e to the minus gamma z plus some v0 minus e to the minus gamma z. That's the general solution. I can get it for you by doing a Laplace transform, or I could get it for you by simply doing an assumed solution and plug it in and solve for gamma in terms of the constants I selected. But getting back to this thing, right here. This is important. Last time I was mentioning this. The first one, that plus sign gives it away. This is a wave traveling in the plus z direction. Y'all follow me on this? So this represents, it's a phasor form of an electromagnetic wave moving in the positive z direction. And this is a phasor form, the second part, of a wave moving in the minus z direction. Now, I can prove that pretty easy, but remember, that's the phasor form, right? Phasor means we're assuming we're in that crazy j omega space, right? We've done a transform, we're there. If we wanted to bring it back to the time domain, do you remember what I told you to do? There was a general relationship between phasor and time. Anybody? Anybody at all? Well, what did it have to do with it? It said V, if I wanted it in the time domain, would be ZT, would be the real part, right, of the phasor form. I could take both of them. I tell you, I'll do it both of them now. It would be V0 plus E, and then here I'm going to do something. I'm going to replace that gamma with alpha plus J beta. I'll try to make this a little neater so you see it. So this is going to be the real part of V0 plus e to the minus alpha z, e to the minus j beta z, times e to the j omega t, right? Because I have to bring in e to the j omega t. And it's going to be plus V0 minus e to the plus gamma z, e to the plus j omega t, j beta z, and then e to the plus j omega t. Now I have to take the real part of it. Y'all remember doing this, right? E to the j omega t is a thing you multiply the phasor by, and then take the real part of what results, correct? And we use Euler's identity for this, and if you look at this, these two coefficients can be added together, and these two coefficients can be added together, right? That's the only place that has an imaginary possible term, right? The e to the j business. The e to the minus alpha is strict real. So when I do this, I'm going to do something. I'm going to put the solution for this right here, up here, so you can write it a little better. When I do this, I find out that V of z, comma t, is V0 plus e to the minus gamma z cosine of omega t minus beta z plus V0 minus e to the plus gamma z times cosine of omega t plus beta z. And again, this is a wave traveling in the positive z direction. This is a wave traveling in the minus z direction. Now, since they are, this waveform is defined for all space, isn't it? If I have a cosine of omega t minus beta z, it's everywhere. You pick a value of z or t, something exists, right? It'll have nulls, it'll have values of 0, but it exists everywhere. So how do you prove that it's actually propagating that way? Well, what you do is take a look at the phase velocity. Remember phase velocity? And for this one right here, the phase velocity, how many remember how to get the phase velocity? Anybody? Do you remember me doing it at least? What did I do to get phase velocity? Anybody? Well, the hint is phase. Do you all agree that's the phase right there? That's phase. Velocity is always something to do with the rate of change with time. So if you take a derivative of that with respect to time, you get omega minus beta dz dt equals 0. Correct, class? Just look for this. Do y'all remember me saying that? Well, then you take omega to the other side, and you see that when you do it, you get dz dt is equal to omega over beta. That's positive. It's moving in the positive direction. Y'all hear me on that, class? If you do the same thing over here, that's moving in the minus z direction. Y'all follow me? It's the phase. And this is one other thing. Another way you can do this, and I'll just tell you this, because I sat where you sat years and years ago. if you plot that waveform versus z for say t equals 0, just plot it out a couple of periods, and then you increment t by a small amount, say t is millisecond or a microsecond, something very small, and you look at how the peak shifts, where the peaks are, and in the direction the peak shifts is the way the wave is moving. Y'all hear me on that? That's just a tip for later on when you have to deal stuff with crazy stuff. This is fairly simple, but some of the stuff with wave equations, you can't tell what's going on until you plot it versus time for a couple of different times. Anyway, that's the general form of the solution that you get from the assumption that we're at a constant frequency, and this is the model of the transmission line. So you get that, and I'm going to tell you one other thing, and I'm going to use this middle board here to do this. And I'm going to do this. You did that everything with respect to voltage V. That's the voltage difference between the upper and lower contact point on the transmission line. Next, get this. I'm going to leave those equations up and I'm going to just show you. Now I'm going to show you the equation that results if you look at only I. Suppose I take this equation and take another derivative with respect to z. Y'all hear me? So what am I going to get? Well, I get the second derivative of I with respect to z is equal to minus quantity g prime plus j omega c prime times dv dc. Y'all agree with that? How many see where I'm going with this? Come on, you guys have to see. You won't admit it. Yeah, what am I going to do next anyway? Sure. I'm going to take what? Right? And I'm going to put that where dv dz is. Do y'all agree? As a matter of fact, I'm going to just erase it right into it. So I write that down, and I have another minus, so it gets rid of that minus. And you'll notice that this has the exact form of the equation that the prior one did with voltage. Do you all see that? As a matter of fact, it is a replica in every way. So now I have the second derivative of I with respect to z squared minus gamma squared I equals 0. You can get this by just substituting in gamma squared for that g plus j omega c times r prime plus j omega l prime. You get a gamma squared there and taking it to the other side. The solution for this is just like the prior solution. I will be equal to some I naught plus e to the minus gamma z plus I naught minus e to the gamma z. And this is a waveform traveling in the positive z. This is a wave traveling in the minus z. And both the current and the voltage are linked to each other. The value of one gives rise to the value of the other and vice versa. And I'm going to show you the linkage. It's done so by something called the characteristic impedance of the line. Can you all see this okay, by the way? In the far back? Okay. Now, when you do this, the next thing I'm going to say is, I'm not going to go ahead and put the time domain form. It's identical as before, all right? It's just instead of V, you're going to have these I's here. Now what I'm going to do is find the relationship between I and V, and I'm going to start by taking a look at this equation, and I'm only going to look at the positive traveling wave, or else these things get a little lengthy. So I'm only going to look at waves that are in the plus z direction. That means my V is some V0 plus e to the minus gamma z, and my I is some I0 plus e to the minus gamma z. Y'all follow me on this? So now I go for it and find out what the relationship is. I'm going to take that v equation that I have there, take a derivative with respect to z, and equate it to that. So when I do that, I have, well, the derivative of this with respect to z would be minus gamma v0 plus e to the minus gamma z. Remember, I'm taking a derivative of this equation with respect to z. Y'all follow me? In doing so, I have to bring the minus gamma out. Y'all follow me? You good with that, guys? All right. That's equal to what's on this side. The minus r prime plus j omega L prime times I. But what is I? It's this. So I put that value in. I'm going to let you just copy it down before I continue on. Y'all follow the rationale behind this. I'm using the defined equations, the differential equations, to develop this relationship once I know the assumed solutions of them. All right, now watch. What I'm really after is the ratio of V0 plus to I0 plus. That's my goal. Take a look at this for a second. Y'all see how that e to the minus alpha z does nothing? It appears on both sides. Can y'all see that, class? Can't I just get rid of that? Divide both sides? But sure. So I get rid of this first. What else can I do? Anybody? Take one look. It should be very apparent to everybody. Get rid of the minus. I hate minus signs because they look like scratches to me, and I'm getting old. My eyes don't work. So I circle minus signs when they're important, and I get rid of them if I can. I'm going to get rid of this one. It's on both sides, multiplied by minus 1. What next? I want the ratio of V0 plus to I0 plus. So what happens when I have V0 plus over I0 plus? That's equal to R prime plus j omega L prime over gamma. All right, and by the way, this is called the characteristic impedance. And the symbol is Z0. Now you can put a plus there since if you want, it's a ratio of V0 plus to I0 plus. And then when I substitute in for gamma, this is equal to R prime plus j omega L prime over, and then this would be the square root of R prime plus j omega L prime times G prime plus j omega C prime. Can you all see that? When I replace gamma with the definition? Now take a good look at that. There's something that'll simplify very easily. Can you all see it? Take a look here. You see how I have R prime plus j omega L prime here? And I have R prime plus j omega L prime here, correct? But this is to the 1/2 power. So that means in the final result, when you divide out that, you end up with, and I'll put it right here, Z0 plus would be equal to the square root of R prime plus j omega L prime over G prime plus j omega C prime. And that is the ratio of V0 plus to I0 plus. And that's important. That's called the characteristic impedance. Now I'm going to come over here and do a few things. There's one thing that's important to note too. When you're doing this, you'll notice that this is a ratio of voltage to current maximums for positive going waves. You all hear me? However, if you were to do the same process for the negative going waves, you would get the ratio of V0 minus to I0 minus would be equal to minus Z0 plus. All right, so it'd be equal to minus that right there. Or it would be minus the square root of R prime plus J omega L prime over G prime plus J omega C prime. And that's important. You'll see why in a bit. So now, when I have that, what I'm going to do next is this, because I want to follow Whitworth's books, the way he's outlined this stuff. When you look at this, doesn't mean a whole lot until you see some applications of this. I'm going to get there in a second, but I got to do one other thing. So when there are lossless lines, lossless T lines, or very low loss lines, that's common. You wouldn't want a transmission line that had a high loss if you didn't have to have that. Transmission lines are to really conduct either information or power. So you don't want loss, much loss, but loss is inevitable. And this is a general form. But if we talk about a truly lossless line, or a line that could be approximated with that, then the characteristic impedance Z0 plus, which is the ratio of V0 plus to I0 plus, becomes simply the square root, if you look over there, of L over C, L prime over C prime. Now guess what? When you have a coaxial cable, you all know what coax is, right? Coaxial cable. All right, you read on there, it'll have a ratio. It'll say either 50 ohm or 75 ohm, something like that. Now Spectrum and the old Charter and almost any cable provider in this area has cable running to your house at 75 ohm. There's a reason for it. It's very low loss. That's the reason. And that cable, what that means is the ratio of the square root of L to C per meter is actually 75 ohms. Everything we do with microwave engineering in the labs, building things, testing things, is 50 ohms. That's just the standard. The ratio of the square root of L over C per meter of that cable is equal to 50 ohms. It has absolutely nothing to do with the actual resistance of the cable. You all hear me on that? Now, and this is one of those things that people make mistakes. I've seen also, well, shouldn't say I've seen, I've observed people do things that were based on horrendously false assumptions. Like 78 ohm speakers mean that the speaker itself is 8 ohms, and if you ever put a battery across a speaker coil, you'll notice you'll fry it because it's not 8 ohms, all right? Now, what it is it has to do with the characteristic impedance of that speaker coil at a certain frequency. I'm not going to go there, but there are a lot of things that happen based on false and foolish assumptions. Now, with that in mind, what I just said, that's the characteristic impedance of the line. There is something that has to be said for how long of a line has to be there before it actually has that impedance. And here I'm just throwing something out that's a little further down the track. If you had a coaxial cable as such, all right, and it was lambda over 40 long at the frequency, it isn't 75 ohms between these two. Now this is just a straight piece of wire, two straight pieces of wire. You all follow me on that, class? When all of a sudden the cable will behave as having a characteristic impedance of 75 ohms is when the length of this line segment becomes a 1/10 of a wavelength or longer. It's not abrupt, but after a 1/10 of a wavelength, the ratio of voltage to current is closer and closer to the actual characteristic impedance. Do y'all hear me on that? Just listen to me, because here's what people do. They have a 75 ohm cable and they connect it to something and they do their engineering, and you're going to see how we do T-line engineering, and it says it should be matched. They don't realize that the length of this thing is only maybe 1/30th of a wavelength. Effectively, they just soldered on 2 pieces of wire. There's no characteristic impedance to that. So just be aware of this. This is a common mistake. That comes later, but I just wanted to tell you it now. So characteristic impedance of these lines, a line can't be viewed as having that kind of a characteristic impedance unless it's at least of a 1/10 of a wavelength long. Now, back to lossless lines. Dr. Whitworth does this. He says, well, if you have a lossless line, that's the characteristic impedance, and it's constant, and it's just a ratio of L over C if it's lossless or low loss. Something else. Do you remember what phase velocity is? Do you remember the fundamental definition, anybody? I developed this last time, but I didn't give you a problem with that. Remember how I got it? I took omega t minus beta z and I set it equal to what? A constant. And I took a derivative of that term with respect to t, right? And I solved for dz dt. Do y'all remember kind of that? And I found out phase velocity was what? Omega over beta, didn't I? Remember that? And when you found that, the key thing here is beta, isn't it? So now, take a look. We're going to look at the lossless form. This is going to be for all lossless things. When we have gamma as a square root of r plus j omega L and g plus j omega c, well, if it's lossless, just look. If it's lossless means no resistance, no conductance. That's the implications. So if you have no R and no G, isn't this thing just J omega square root of L prime C prime? Take a good look. Do you all agree with that? Convince yourself. You agree? Now what is gamma? Well, that's alpha plus J beta, correct? So what can you conclude about alpha for a lossless line? It's 0, right? There's nothing there. Do you all follow me? The coefficient, there is no real part but 0. So alpha, if it's lossless, is 0. Makes sense. What is beta? Class? Anyone? Everyone? Come on. Sure, it's just omega square root of L times C, right? So it's omega square root of L prime C prime, right? So what's the phase velocity? Well, it's omega over what? Over omega square root L C. Can you all see this? So it's omega over omega square root of L prime C prime, or it's just 1 over the square root of L prime C prime. Remember that. Okay. Just trying to show you the simple way to get this stuff. So that's phase velocity. Next, I'm going to say something that I'm going to put it right here too. When we're talking about, this doesn't have to be lossless. Now let me get rid of this, but I want to show you the way it's most commonly, most of this stuff is most commonly rendered in the book and other places. What time do you guys have?
12:37.
Time's flying. Okay. When I take a look at this, this is something I want you to remember. Normally V is some V0 plus e to the minus gamma z, e to the minus j beta z. And V0 minus e to the gamma z, if there is a negative traveling wave, times e to the minus or plus j beta z. And again, this is positive traveling, positive z, this is minus z. Now I this is in the phasor domain, will not be I0. What it will be given as V0 plus, all right, over the magnitude of Z, characteristic impedance, or you can write it as just, for now you can write it as just Z0 plus, because remember, the ratio of voltage to current is the characteristic impedance. Y'all with me on this? So we don't write I naught, we do this way. And then it would be e to the minus alpha Z, e to the minus j beta Z, and then here, there'll be a minus sign, because I told you the ratio of V0 plus to I0 plus was minus Z naught. Do y'all remember that? So then it will be minus right here, and it will be V0 minus over Z0 plus, and then it will be e to the alpha Z, e to the j beta Z. Now just remember that. Now I got one more thing and then we'll do the problems. Let me show you. Y'all with me? Okay, now, finally, last thing I want to talk about today is power. Anytime you have a coaxial line or any transmission line, as such, two-conductor line, this is power. And we have a given current I flowing down and a given voltage V across these terminals. There is some net power flow. We're always worried about average power flow. We don't care about peak, but we care about average if we have a sinusoidal variation of the excitation. So when we talk about average power, that's equal to 1/2 the real part of V times I conjugated. Now, when you had circuits, do you remember how power was defined for DC things? It was what? Just I squared R, V times I. There was not a half in there. Do y'all remember that? But here, because we're dealing with quantities where we're not using RMS values of voltage or current for I naught and V naught, what we have to do is include this 1/2. These are peak values, so it's 1/2 the real part of V times I conjugated. Are you with me? I'm going to write this down, and for sake of sort of saving a whole lot of space, I'm only going to be talking about positive Z going waves. So if we only talk about waves in the positive Z direction, we find out that the average power is equal to 1/2 the real part of V, and that's just V0 plus e to the minus gamma Z, e to the minus j beta Z. Then it's times I conjugated. I'm going to write I and then I'm going to conjugate. So I is V0 plus over in here, it's got to be the magnitude of Z naught here. And the let me explain this. Remember how it was V0 over Z0 plus before, class? Right? Right, Z0 is a complex number, possibly. That means it has a magnitude Z0 plus, and it's got a phase angle. The phase angle can be written down here as e to the positive j phase angle associated with Z. Can you all follow me? You can put the phase angle like that, but if we take it up top in the numerator, then it would be e to the minus, and it would be the phase angle, or it would be minus j, phase angle associated with theta Z. Just call it that. That's the phase angle here. It's that, so that's like I naught, and it would be e to the minus gamma Z, e to the minus gamma Z, e to the minus j beta Z. That would be what the current would be right there, but I didn't conjugate it yet, so I'm going to show you what happens when I conjugate it. Can you all see that, class? How in the back, you see, guys see this, I'll never know, but you're better than me. Anyway, you all with me on this? Now, what does conjugation mean? If I have a quantity A is equal to 1 plus J1, what is A conjugated, class?
1 minus J1.
Yeah, 1 minus J1, right? What about if I had A equals square root of 2 at an angle e to the j 45 degrees. What is A conjugated? Class? Just say it.
Root 2 e to the minus j.
Sure, square root of 2, the angle changes sign, e to the minus j 45 degrees. Y'all follow me in that class?
Yeah.
That's conjugation. You all know conjugation, right? I mean, this is a term that you're going to hear over and over again, so you get familiar with it. So when I take the conjugate of this, all the real terms, that means no j's in them, you don't do anything for it. That means the v0 plus, the magnitude of z naught, and e to the minus alpha z you leave alone. You all hear me? And everything with an imaginary term, if it's an angle, if it's got e to the j in it, you flip the sign. So that means this sign becomes positive and this sign becomes positive. Are you with me? I'm just trying to show you the thought process. When you do conjugation, you simply flip the signs on the j's, e to the j thing, right? That's it. Now, take a careful look at this just for a second and you'll see what's going on. You'll see right here, I have e to the minus j beta z. Can you see it? Then it's multiplied by e to the plus j beta z, right? You know you can add the exponents, so it's e to the plus j beta z minus j beta z, or e to the 0. What is e to the 0? 1, so I get rid of it. Never liked it to begin with. Now, can you see you have e to the minus alpha z times e to the minus alpha z? That's e to the minus 2 alpha z. I'll write down the answer to this over here. All right. So this will be equal to 1/2. And then I've got V0 plus, that's strict real, so that can come out in front. V0 plus squared over the magnitude of Z0 plus. That's all real. And then I have e to the minus 2 alpha z, that's all real, e to the minus alpha. So I'm taking the real part of something real, just pull it out in front. Here's where I need to worry. I have the real part of e to the j, the phase angle of the impedance, characteristic impedance. And to get the real part of that, I have to take the cosine of that angle. So it's times the cosine of the angle associated with the characteristic impedance, right there. And that is the average power flow in a transmission line. And the units of this would be watts. Average power is in watts, W-A-T-T-S. Y'all follow me? It's straightforward. Now I want to do the homework problems that I've assigned you. How many actually took a look at them? All right, if you looked at them, can you give me the first problem? I think it was 6, wasn't it? Let's do 6, if you don't mind. And I'm going to erase this and do it. I'm trying to get these done. Oh, I had to go through this theory. So what does it ask for? That there. So what is it, problem 2-6, class? Can you tell me what it is? You have it? No? All right. Usually the class is interactive and it helps everybody because they'll get a lot of questions directly at me that other students will answer. The impedance, so this one is, the characteristic impedance is given and gamma is given. This one's not the one I like, but we'll get it. So can you just tell me what characteristic impedance Z naught is? And gamma?
Z naught is 18.6 minus J 0.253 ohms, and gamma is 0.0638 plus J 4.68 per meter.
4.68?
Yes.
All right. Here's one thing I always recommend. Anytime the answer just doesn't jump off the board at you how to do this, what are they after? They're after what? L prime, C prime, G prime, and R prime, right? They're after the per meter parameters, correct? The way you get this is always think of how these things have been defined in terms of what they're asking for. So Z naught, the characteristic impedance, was equal to the square root of R prime plus J omega L prime over G prime plus J omega C prime, right? And gamma was equal to the square root of R prime plus J omega L prime times G prime plus J omega C prime. Can you all follow me on that? I'm just showing you the thought. Now, look for a second and think. Oh, they also give you the frequency, don't they? F, I forgot what it is. Anybody?
100 megahertz.
So it's 10 to the 8th hertz, which means omega is 2 pi times 10 to the 8th hertz, right? Class? Now look, when I have this, what happens if I take Z naught times gamma? Just take a look. Well, I just get R plus J omega L by itself, don't I? Take a look, isn't that right? Take that, Z naught, and multiply it by gamma. You'll notice how you get square root of R plus J omega L, square root of R plus J omega L equals R plus J omega L, and the 1 over square root of G plus J omega C cancels. Do you all see that, class? How many see that? All right, so now I have this. You'll notice I can easily multiply these with calculators or computers, right? I can easily do that. So the real part is just R, and the imaginary part is this, where I can figure out L straightforward. Can I, class? By what? Dividing the imaginary value by omega, correct? Now what about getting G and J omega C? How would you get it? Take a look. Well, if we multiplied and got that, what do you think happens if we divide? Let's divide Z naught by gamma. What do you get? I could do this a couple ways. If I take Z naught divided by gamma, what am I left with? I'm left with what? 1 over G prime, right? Plus J omega C prime. Or if I have gamma over Z naught, I'm left with G prime plus J omega C prime. Do you all see that, class? How many say this right here? All right, now can't you, just taking a look at that, the real part of doing that operation based on that value, so it will give you just G prime, and the imaginary part you have to divide by omega to get L prime. Now, those are things that are, at first, I didn't see it right off the top, because you're not used to dealing with these equations. But when you get used to them, it'll be self-apparent to everybody that does their homework, okay? One last thing. I'm over by a minute. With power, I want to make one comment. How many have heard of decibels? All right, in your labs, did you get that? Let me just put this down. When you're dealing with dB, power in dB is equal to 10 times log, and that's a base 10 log, that is not log base E, of any quantity. And when you're dealing with either voltage or current in dB, it's 20 times the log of either V or I. And it can be something where you have a dB. How many have heard of dBm in here? Okay, dBm is simply a power quantity, but it is normalized to a value of 1 milliwatt. So power in dBm is 10 times log of the power quantity divided by 10 to the minus third, or 1 milliwatt. That's all it is. Now, I'll put down some more stuff. I'm sorry I'm out of time. I'm trying not to rush here. And I'll give you some more homework, and then we have Monday off, don't we, class? So on Wednesday, we'll pick it up. Please do the homework and get the book. All right, anything for the good of the group from anyone? You're dismissed technically. You're over, but I owe you a minute. Did you all understand this lecture?